So we will continue our discussion with a testing for conflict serializability. So the algorithm will test for serializability and it will verify whether there any conflict arises between the transactions or schedules. So here in while testing for conflicts, so we will only look at read and write operations in a schedule. So based on that, uh, we'll construct a precedence graph that is one node for each transaction plus directed edges will be there. So an edge is created from a transaction I to transaction J if one of the operation in I appears before a conflicting operation in J. And the schedule is said to be serializable if and only if precedence graph has no cycles. So the complete algorithm is here. So testing for conflict serializability of a schedule, yes. So in the first step, for each transaction Ti participating in the schedule, we will create a node labeled Ti in the precedence graph. So one node is created for each transaction. Then for each case in a schedule where a transaction J execute a read X after Ti executes a write X, then we will create an edge I to J. So if a transaction I is writing and transaction J is reading the same variable X, then in the precedence graph we will draw an edge from I to J. Then for each case in a schedule where J executes a write after Ti executes a read, then we will create an edge from I to J. So in the third step, it is again creation of an edge from I to J when J is writing and I is reading. So it's a reverse. In that case also we will create an edge from I to J. Next, for each case in schedule S where J is writing after Ti executes a write operation. So here both are executing the write operation. So Ti is executing first, then Tj. Then also we will include an edge from I to J. So in these three cases, Ti is the one which is executing first. So when Ti executes, when it read or writes and the other one does the opposite, then an edge is created from I to J. The only case where an edge is not created is when both of them performs the read operation. So after creating such a graph, so the schedule is said to be serializable if and only if the precedence graph, whatever we write, has no cycles. So a graph is said to have a cycle when we start traversing from one node and reach the same node. And here the graph is directional graph. So here is the pictorial representation of those edges T1, T2, and this indicates there is a dependency. So X is the variable on which this graph is written. So this is how constructing the precedence graph for a schedule A to D for conflict serializability. So consider this example for serializability testing. So here we have three schedules, so A, B, and C, and each having three transactions. So first, consider the example A, transaction 1, 2, 3. So read X, write X, read Y, write Y. So on the other end, read Z, read Y, write Y, read X, write X. So here read Y, read Z, write Y, and write Z operations are there. So for these operations, now we can write a graph. So since there are three transactions, so first we will write three nodes. So consider this particular examples. Okay, here two schedules are given. So schedule A and schedule B. Okay, they are same. So the only thing difference between A and B is they are just interleaved. Okay. So apart from that, both are same. So here, if you we can consider any one and draw the graph. Okay. So let us consider this one only, A only. So here three transactions are there. So we can draw three nodes. So for T1, one node, uh, T2 another one. Let us draw one more here for T3. So three nodes are created for these three transactions. So next here, observe one variable x between transaction 1 and transaction 2. So here it is reading, here it is also reading, here it is write operation. So which is the first transaction that is dealing with variable x? So it is transaction 1. So here transaction 1 is writing, and here the transaction 2 is reading. So which one is occurring first? So that is the transaction 1. So there should be an edge from transaction 1 to transaction 2 for the variable x. So we'll write like this. Then look at the read operation. So read y, write y. So here if you observe, so read y, write y. So here we have a write y operation, and here we have write y operation. So and which one is happening first? It is in the transaction 2. So transaction 2 writes y first, so there should be an edge from transaction 2 to transaction 1 over variable y. So next look at transaction 3. So it is reading y, here reading z, writing y. So again if you observe here, here it is writing y, here it is reading y in the beginning. So the first transaction that is happening on y is in transaction 3, where it is reading, and here transaction 2 is again writing. So from transaction 3 to transaction 2, there will be an edge on variable y. Okay. And here once again we can look at this particular operation. So or here there is a write operation, And here read operation. After read operation, there is one more read operation followed in transaction 2 over here. So read, then followed by read operation, then followed by write operation. And this is happening in T3, this is in T2, this is in T3. Okay. And then we have one more write operation that is happening in, okay, this is T2. So in T3. So if you observe here, read followed by a read, and these two are in same transactions, and write after write. So it is transaction 2 write and transaction 3 write operation. So from 2 to 3 there should be an edge for variable y. Then look at variable z. So the first time the z operation that is happening is in transaction 2, that is a read operation. So that is happening in 2. This is for z. So read is happening in T2. Then it is again read in T3 and again write in T3. So but these two are in same transaction. So read followed by a write. So which is the first operation that is happening? That is T2. And hence there should be an edge from T2 to T3. So next consider transaction T1 and T3. So it is dealing with x and y. Here it is y and z. So on x there can be no relationship. So now on y, so it is read, write. Here it is read, write. So the first operation that is happening in uh, transaction T1 and T3 is read, that is happening in transaction 3. Then it is read in T1. At the same time, it is write in T3. So there will be a relationship. So we can have an edge from T3 to T1 on variable z. So the final graph will look like this, and if you look at this graph, there is a cycle over here. So if cycle is there, so we can say that it is not serial. So in the second example, so this is regarding um, this schedule F. So in schedule F, so if you are confused with uh, this particular schedule, then you can check the B table where the operations are interleaved. So that will clearly tell the which operation is happening first and which is happening second. So based on this particular B, you can write the graph, because it is not clear in A which operation is happening first and which is happening second. So based on this B, we can write the graph. So now similarly consider this one. So the schedule F. So in schedule F, again there are three transactions. So since three transactions are there, again we shall write three nodes, so T1, T2 and T3. So we were writing for this particular schedule. So here, so now consider variable x is over here. So it is present here. Okay. So write followed by read operation. So you can clearly say it is the transaction 1 that is initiating the operation on x first and then it is T2. So can we have an edge? So there will be an edge from uh, T1 to T2 over variable x. Now again if you look at the y variable, so read and write, here it is reading, here it is also reading and writing. So you can see over here. So it is the transaction 1 which has initiated the read and write operations on variable y. So we can have an edge from T1 to T2 over y also. Next, um, there is no z in transaction 1, so it doesn't occur. Now look at transaction 1 and transaction 3. So transaction 1, it is reading y. So here it is writing the value y. Whereas the transaction 1, it is reading and writing y later terms. So it is transaction 3 that is first dealing with variable y. So there will be an edge from 3 to 1 on y. So next, so transaction 3 is not having x, so it's over. Now compare T2 and T3. So when we compare T2 and T3, so it is read z, here also it is read z, but here we have a write z operation. So since we have a write z operation over here, here it is read z. So clearly the first operation that is taking place over z is in transaction 3. So from 3 we can have an edge to T2 on the variable z. So next, and variable y also, so here it is read, here write, and here it is reading. So again clearly for y also the operation is taking place in z in transaction T3. So we can write an edge for y also from T2 to T3. So this is the complete graph. So for this particular one, so does this graph contain a cycle? So that's the question. So this graph, if we start traversing from T1, can we reach T1 back? So since the edges are directional, so we cannot reach T1 back. So if we start from T2, we cannot reach any nodes. So if we start from T3, again, we cannot reach back T3. The sequence of traversal we can write is, so T3, T1, then followed by T2. We cannot reach back. So since this is, it contains no cycles, so we can clearly say this is serial. So this is the graph for all the uh, things which we discussed. So next we discuss the concept of view equivalence. So a view equivalence is a less restrictive definition of an equivalence of schedules than the serializability when blind writes are allowed. In view equivalence, blind writes are allowed. So blind write is nothing but it is a write operation without performing a read operation on the same variable. So if that blind write is allowed, then we can say view equivalence is possible. So view serializability. So it's a definition of serializability is based on view equivalence. Then we say it as view serializability. So a schedule is view serializable if it is view equivalent to serial schedule. So there are various kinds of serializability. So one kind is view serializable. So a schedule is said to be view serializable if it is view equivalent. So two schedules are said to be in view equivalent if these three conditions are met. So we say that two schedules are view equivalent if the same set of transactions participate in both the schedules and they include same operations on those transactions. For any operation read in transaction I in S, if the value of X read was written by an operation J on the same variable in an operation in a transaction J, the same condition must hold for a value of X read by ith transaction on S dash. So which means if one transaction is reading, another one is writing, the same situation should arise in another schedule also. So here we are comparing two schedules. So if an operation uh, write on a variable y of a transaction k is the last operation to write the item y in one schedule, then this must also be a last operation in another schedule also. So the reason behind view equivalence are to consider view equivalence is each read operation of a transaction reads the result of a same write operation in both the schedules. So the view indicates that read operations are said to see the same view of both the schedules. So here it is with regard to the read operation, the schedules are compared. So when an operation reads the value in both the schedules, the value that they read should be same. So the final write operation on each item should be same in both the schedules, resulting that in the final result of the database is same, even in case with blind writes. So here in view equivalence, the final result should be same, and whenever the read operation performs the action, the read value should be same in both the schedules. And even in blind writes, the final result should be same. So the relationship we can establish between view and conflict equivalence. The two equivalences are constrained under right assumption. So if there are no blind writes, so then we can say it is conflict equivalent. No blind writes are allowed. So conflict serializability is very strict than view serializability when blind write occurs. A schedule that is view serializable is not necessarily a conflict serializable, but the opposite is possible. So if a schedule is conflict serializable, then it indicates it is also view serializable. So the relationship again, consider the schedules over here. So of a three transaction, T1, T2 and T3. So T1 it is reading and writing, T2 is just writing and T3 is just writing. So here in transaction 2 and 3, it is a blind write. So they are not reading, but they are just writing. So a schedule can be written as read X, write X, write X, write X, but here 2 is in the beginning and then the processes are committed. So in this particular schedule, the operation write X in transaction 2 and write X in transaction 3 are blind writes. So since T2 and T3 are not performing the read operations. So this particular schedule can be view serializable since it is view equivalent to serial schedule T1, T2 and T3. However, this particular schedule is not conflict serializable because in conflict equivalence, blind writes are not allowed. So other type of equivalence that can exist. So we have discussed conflict equivalent, result equivalent, and then this view equivalent. So under special semantic constraints, so schedule that are otherwise not conflict serializable may work correctly. So using the commutative operations of addition and subtraction, so certain non-serializable transactions may work correctly. So that is known as debit and credit transactions. So if there are these are the addition and subtractions are the only operations that are being performed in the transaction, then we can say that irrespective of the order of addition and subtraction, the end result of an arithmetic operation will be same. That's why even though if the schedule cannot be serializable under the conflict, so they can be made as they can be made as a serializable transaction if they are debit credit transactions. So debit credit transactions are the one which have only addition and subtract operations. So and this is allowed under semantic constraints. So consider the bank credit and debit transaction on a given item, so which are separable and commutative. So consider the following schedule. Yes, for two transactions, so read X, write X, read Y, write Y, then read Y, write Y, read X, and write X. So using conflict serializability, this is not serializable. However, if it came from a read, update, and write operations are performed, so that is, if the operations are just addition and subtractions, then the order in which you perform the operation, it doesn't matter. At the end of both the transactions, the value of X and Y will be same. So if the end result of X and Y is same, then we say it is semantically equivalent. So here the operation that is performed is X minus 10, Y minus 20, Y plus 10, and X plus 20. So now the order in which it is performed, so it doesn't matter. So and it follows a correct schedule for a semantics. But if multiplication, division, and other operations, non-linear operations are involved, then we cannot apply the semantic equivalence. Okay, so this is with regard to the transactions. So in from next class, we shall study how transactions are supported in SQL. So you can enter your attendance.